Welcome to this second session on Boolean Algebra, where we began to look at some of the laws that apply. Now, there are many other laws in ordinary arithmetic that also apply in Boolean Algebra. Say, for example, the commutative law and the associative law that we normally have in ordinary mathematics also apply here. So we'll take a look at these laws here. So, again, we'll look at Boolean laws and theorems. We'll define the exclusive OR. We'll try to see how to simplify Boolean expressions, and then giving a word description of a desired behavior of a network, we can write out this as a function. And then we can look at min terms and max terms. So there are four things I want you to know. Some of the laws of Boolean algebra, De Morgan's theorem, Boolean functions, and how to reduce these Boolean expressions. These are the four things that you must know. You are required to read chapter 3 of the recommended test, which is Fundamentals of Logic Design. So, laws of Boolean algebra. Let's look at the commutative property. So, if you have A and B in a set K, then A plus B is the same as B plus A. And A and B is the same as B and A, or multiplied by A. So in other words, A or B is the same as B or A. And then A and a B is the same as B and an A. In other words, it doesn't matter the order in which you do it. The associative property. Here, for every A, B, and C, then A and into brackets B, A or into brackets B or C, brackets close, is the same as brackets A or B, brackets close, or a C. Or the other one will be A and into brackets B and C, brackets close, is the same as B, brackets A and B, brackets close, and a C. In other words, if you have or an and of three operators, it doesn't matter which one you do first, the order in which you do them. We can write the circuits to represent this, such as in the first one, A and B, and then you what? End that with a C. Or you can use a 3-input circuit to represent the same thing. The same way we can use the OR one as well to represent them. And then we also have the distributive property. Right? So if you have A and you end that with a B or a C, then it's the same as doing A and a B or A and a C. That is, you sort of multiply out. And then the other one will be A or B and C will be the same as A or B, and you end that with A and a C. These are things you can verify for yourselves, by looking at the truth tables, for example, writing the truth tables for this. Now, it's important to note that for every element, there is this unique element called the complement. So for every element, the complement of it would exist. What you should note is at times, to simplify the notation, the dot between the ends may be omitted. So if you have A and not A, you may simply write this as A not A. You omit the dot there, just simply to simplify the operation. So you know that when you see the two elements written next to each other, you must assume that it is an AND operator that is implied. Now, if you have X and x, y, and z, that is x and a y and a z, then that will be equal to 1 if and only if x equals to y equals to z, and that is equal to a 1. The same way, if you had an x or a y or a z, and that is equal to 0, that would happen if and only if x equals to y equals to z, and that is equal to 0. Then there's also the principle of what? Duality. This says that if an expression is valid in Boolean algebra, the dual of that expression would also be valid. To form the dual of an expression, replace all the plus operators with what? The AND operators, and all AND operators with what? Plus operators. With all ones with zeros and all zeros with ones. You know, I hope that is clear. So to form the dual, just replace everything with the opposite. So to form the dual of the expression A or B plus C, so what do? We replace the AND operators with all operators, and all operators with AND operators. So then this becomes A or B into brackets A and or C. The same way, you can do the similarity for that. You know, you've got A into brackets B or C, the dual of it, you know, you can write down. Involution. A double negation becomes the number. So not A is an A. So taking the double inverse of the value will always give you the initial value. There's also the absorption theorem, right? Which is if you have A plus A or B, then the answer is A. And then if you also have A into brackets A plus B, then the answer is A. Well, you can prove this, you know, to show that you know, you can write that as A plus AB, right? The A becomes the same as what? You know, A or a 1 plus AB, right? You can then take the A out of the brackets. So if you add a 1 to any number, the number is a 1. So the proof is simple. And you can try proving the second one as well to see if it is true. De Morgan's theorem is quite useful when you try to simplify Boolean algebra. Now, what it states is that if you have A plus a B into brackets negated, then that's the same as not A and not B. And then if you also have AB all negated, then that's the same as not A plus and not B. So using De Morgan's theorem, you can attempt to simplify the expression that is shown below. Right? So you can work through the expression to see what it says, you know, and verify it for yourselves. But it's an important theorem that you should know, because anytime you come to simplify Boolean expressions, this is something that will come in handy. Now let's look at Boolean functions. So Boolean algebra deals with binary variables and logic. Functions results in binary zeros or ones. So if you have a 3-input Boolean function, right, that gives you a certain output, right? Now, we can then write or draw a circuit that represents this. Yeah, we know that we only get an output of 1 in 3 circumstances. You know, when x is 1 and y is 0, z is 0, and then when x and y are 1 and z is 0, and then when all 3 inputs are 1. So a circuit that will represent this, will do this function, is shown onto the side. Now, you would ask yourself, okay, but what exactly is this thing doing? Right? What exactly is it doing? We can think about, or if you like, you can think about a word expression that would fulfill this function for you. Another example is shown where you have a certain output, G, we have intermediate outputs, and then the output function. The idea is that you have a truth table, and then you have, with functions, how do we transition from the truth table to the logic circuit, and then also to the equations. How do you make those transitions? So you're given an equation, okay, you have to get the truth table for it or the logic circuit. So it's important to be able to do these transitions between the circuit, truth table, and Boolean expressions. Right. How do you do this? So given the truth table, the thing is to identify when the outputs are 1. Yeah, so you can sort of circle them. So this outputs is 1 here, it's 1 there, it's 1 there. And then you write the Boolean expression for this. So you get a 1 when x is 0, y, so you get x and a y, or not x and a y and a z. Or you get an output of a 1 when you have an x and a y and a not z. Or you get an output of a 1 when you have an x, a y, and a z. So each row with an output of 1 becomes a product term, and then the sum product bring the terms together. So we then say, okay, so these are the product terms, and then you sum them to get a final output. Now, whether you have it as a truth table or as a product term or as a circuit, they all do the same thing. So in this particular case, right, the circuit for that can be represented as that. And this will be the Boolean expression for it, and what do you call it? This is a truth table. The number of 1s in the truth table output column equals the end terms for the sum of products, or the SOPs. So how do you reduce the Boolean expressions? Now, given that expression we had, the function we had, the question is that the smallest possible implementation of that? Because from that, we obtain a certain circuit. The question then is this circuit the smallest or most cost-effective way of implementing this function? Remember that these things are implemented as circuits on a chipboard, and the number of gates will determine the cost. And also, you want to minimize the number of gates you put there. So you want to keep this as minimal as possible. So is this the cheapest way? The other way to ask, is this the cheapest way of implementing this function? Could you simplify this further? And the answer is yes, you can simplify this further. And there are a number of ways you can do this. You can use Boolean algebra to reduce the complexity. So you can use there are a number of steps you follow. You use theorem 1, where you know that A or an A is an A, so you can rewrite the sum. You can then use the distributive law, some postulates, and then you can show that that function can actually be minimized. So if you did that, then you can show that function can be implemented using just x, y, and yz, which is much cheaper than the previous one. So we can use Boolean algebra to simplify this. So given that, each variable in the Boolean expression, we call that a literal. And then Boolean variables can appear in normal form or complement form. So it's either x or the complement of it, right? Now, when you have that, say if you take the truth table, then a combination of all of them are called mean terms. So x, y, z, or not x, not y, not z, with mean term 0, and then mean term 1, mean term all the way up to mean term 7. And then the max terms becomes the all terms, so x or y or z m0, so the all combinations gives you the max terms, the end combinations gives you the mean term. And we use the capitals, the small m and the capital M, the small m to represent the mean term, and the capital M to represent the all terms. But mostly for this course, we'll be using the mean terms. We'll be focusing on mean terms. How do you represent functions with mean terms? So given the same function, right, then you note that it's this, that, and that which are required to get an output. So you number them, that is m0, mean term 0, mean term 1, mean term 2, mean term 3, and so on up to mean term 7. So then you realize that the outputs required are mean term 3, yeah, because it's mean term 0, mean term 1, mean term 2, mean term 3, mean term 6, and mean term 7. So the function there can be represented as m7 or m6 or m3. In a shorthand, you can say the sum of 3, 6, and 7 to represent exactly the same thing. So it's just a shorthand of representing this. So we can use complementing functions, Morgan's theorems, to attempt to simplify these things. And I urge you to try and do that for yourselves to verify that that is the case. Now, we can do a conversion between the various forms. We can convert between mean terms and max term representations. Now, in the max term, you focus on where the outputs are zeros. So in the mean term, we focus on where the output is 1, but in the max term, we focus on where the output are zeros. So we write that as a product term, as a p term, right? So in this case, the max term is the m0, or capital M0, capital M1, capital M2, and then capital M4, M5, and capital M5. So those are the ones that will give you, so that's the same as P or product into brackets 0, 1, 2, 4, and 5. We can represent all logic expressions using a two-level format. So all the things we've seen so far, we can use a two-level digital format to represent them. So if it's a sum of products, if it's a product of sums, then these circles will represent that. So this is a two-level implementation. So that level 1, and there's a second level. So here you have the products, and then here you sum those products. Here first you sum them, and then you take the product of them. Right. Something for you to think about and work on. Given the following function, show that D is equivalent to E, and then, attempt the rest of the questions. This is supposed to be a proof, yeah? This is supposed to be a proof. Now, there's a flaw in this. What is it? Can you show that what is wrong with this proof? So you can do that. So this is a question you should attempt and see if you really follow this. Again, I refer you to the recommended test, chapter 3 of the recommended test to help you to do this. Thank you, and we'll continue in the next session.